Good morning, afternoon, and evening, everyone. This is Justin reporting in from JSTI Virtual 2021. It's been a busy 2 weeks for the 3D Printing Designing for Strength Research Group. For those 2 weeks, their objective was not only to make things, but destroy them too. Here we have a member of the team live with details.
So, a 3D printer is a system of additive manufacturing, which basically means it's stacking layers on top of each other. In simpler terms, it's really just a hot glue gun held by a robot. And they're great for prototyping because they can create new designs very quickly and are not limited to making things over and over again, like conventional injection molds. So, what you can do with this is, say, make a frog, or you can make more mechanical parts, such as this bear that actually spins.
Tinkercad is a free online program that can be used to create and edit 3D models. The 3D models are then used in a slicing program to make them able to be printed by a 3D printer by converting them to a different type of file.
Now that the boring stuff is done, we're going to move on to the actual gritty part of designing a bridge, right James?
Exactly. We get to choose how our bridge will look and make it strong, using math.
Wow, how exciting.
Well, in order to make a bridge strong, we have to take in all the variables of bridge building and the physics behind it.
So like how the geometry of the bridge affects it? Will certain shapes make our bridge indestructible?
You're right on the geometry part, as certain shapes such as triangles and arches will make a bridge stronger. Our biggest problem is that all bridges are bound to have weak points. So our job is to account for those weak points so our bridge will not suddenly collapse.
Interesting. Well, I'm looking at this first bridge, and it seems that those 90-degree angles are pretty weak. How could we fix that?
Well, now we're getting into the physics behind bridge building. Because those 90-degree angles are obvious weak points, we should work towards fortifying the bridge and lessening the pressure on those points.
Okay. I think I get it now. By adding those holes in that bridge and adding stronger shapes, we're planning for our bridge to slowly fail rather than instantly collapse for safety, right?
Jackpot. Now that our bridge has a stronger shape and will be less likely to collapse to those previous weak points.
Wow, I think that actually really helped. But there's still a few things that I want to fix on that bridge. So I guess we have a bit of work to do, don't we?
Welcome to bridge building. Now over to Kylie and Alma with the bridge testing and the hydraulic press.
Now let's get to the testing. To test these bridges, they used a hydraulic press to exert more than a ton of force, more than enough to crush their bridges.
Their bridges and their dreams, Kylie. Now let's see how their bridges took on that monster in round one.
Round one was a strong start for these young engineers, with more than half of the bridges able to support over 1,000 pounds. At the end of round one, Isaiah's bridge filled everyone with suspension as there was a necessary equipment change. He came out swinging at the end of round one, with his bridge able to support over 1,700 pounds of force.
Wow, that's awesome. I still wouldn't trust that bridge after taco night, though.
You and me both, Alma. In round one, the bridges commonly failed if the corners are broken at thin support near the middle of the bridge. The engineers went back to the drawing board to edit their designs after getting some advice from their mentors so they'd fare better in round two. Speaking of failures, Alma, how about you tell us about round two?
Always a pleasure to be slammed harder than those bridges, Kylie. But as the round two designs show, what doesn't kill you makes you stronger. Most of our engineers are able to improve their designs, with 2 engineers more than doubling the strength of their bridges from day one. Most of the group is able to increase their bridge's maximum load by over 200 pounds. Leading round 2 was John, with his bridge being able to support over 2,100 pounds.
Well, after testing a ton of bridges, here were their best results in overall weight supported and high strength to weight ratio. But we'll have data analysis for you with more of the number side. Over to you, Jordan.
Wood's going. The wood's going. Oh, pop. I cut a piece.
Welcome. This is where we gather all the data from testing. I know it may seem like a lot. Don't be scared. Data doesn't bite. Anyways, let's make this more simple for everyone. I also need to get my steps up. Phew. As you all now clearly see, this is information we obtained, and now you can get the analytics behind how the bridges performed individually through the hydraulic press. The formula we used to find these numbers was dividing by using the formula of the maximum load of the bridge, which is the weight of Upheld, by the mass of the bridge before being crushed. This formula helped us accurately show the strength efficiency of the bridges. As you can see with the graph behind me, there was a varied range of strength efficiencies as expected from the first designs. Let me hand it off to Olivia so she can show us the data analysis of our second batch of design.
Thanks, Jordan. So after revising each of our bridge designs, we crushed them once again and have new data to show you. This bar chart shows the design efficiency of our second design, which had surprisingly mixed results. But let's switch graphs to see them clearly. That's better. So while 3 of our design efficiencies increased, and some by significant amounts of 10 to 17 each, the remaining 7 designs did not improve and actually decreased in efficiency, as you can see by the tall purple columns, which represents our initial designs, compared to the shorter orange columns, which represents our second designs. We have narrowed down the causes of these results to possible issues with slicing, along with significant increases in the mass of our revised bridges. However, looking specifically at the sole maximum weight the bridges upheld, we can proudly say 78% of the revised designs were able to increase their maximum loads. Some shocking results show that one design in particular increased its max from 934 pounds to 2,148. People, that's a 1,214 pound increase. In addition, 3 of our amazing student designs were able to hold a weight over 1 ton. That's as much as the average male American buffalo. We have learned so much from each bridge, crushing, and graph, and have so many new ideas for our next design. But that's just water under the bridge. On to you, Sarah.
Thank you, Olivia. I hope everyone learned something, or at least was amused. I'm Sarah, and this is 3D Printing, Designing for Strength, signing off. The Designing for Strength group would like to give a special thanks to JSTI, ORIUM, ORISE, DITRA, and the Los Alamos National Laboratory for providing us with knowledgeable mentors and the necessary equipment to help us succeed for 2 weeks with JSTI Virtual. We are grateful for this priceless opportunity you have provided us with, which has helped us solidify our passions for STEM.